Hi there. Today we'll look at supermasks and superposition again. So this is part 2 of this paper by Mitchell Wurtzman and Vivek Ramanujan. And here's the reason why there's a part 2. So after yesterday's video on this paper, I couldn't sleep because I really felt that I had left out some important aspects that I wanted to touch on during the video. Now, sometimes during videos, I'll look at the clock and I'll realize like, oh crap, the video is already like an hour long, and I know people are watching on 2x speed anyway, but still it's like too long and I need to wrap it up really soon. And what I felt were pretty important messages about this paper got lost. So specifically, I want to address 3 different things. First of all, they have like a formal analysis, not a formal, but a kind of more rigorous analysis of what their modified G objective does. And I also want to give some intuition in that because I felt I really hadn't done a good job at that. The second part is that the 2 different ideas right here being the supermasks and the superposition. And I think my opinion is sort of that these are 2 separate things and they really have nothing to do with each other. And I think that didn't really come through last video. And the third one being the broader impact statement of this paper, which I usually kind of gloss over it and go like, haha, but here there is an important point to it. So yeah, we'll get to that. All right, so again, not a new paper today, I realize this, but I think it's worth kind of diving deeper into this paper, which is a very cool paper. So don't get me wrong right here. And I feel mostly I haven't done a good part at explaining it, like literally lying awake. Okay, so let's go to the first point. We had this, so if you hadn't seen the first video, supermasks and superposition basically says that we want to do lifelong learning, and we want to do lifelong learning by, lifelong learning is the task where you have a bunch of tasks in sequence and you learn them in sequence, so one after the other, and basically the goal is to not forget tasks once you learn new tasks. And this model does it by always building one of these supermasks for each task that is applied to the same randomly initialized base neural network each time. And by keeping the supermask around, you won't forget the task. And then at inference time, if you're given the task, you can just retrieve the mask. If you're not given the task, you can do this superposition trick where you apply all the masks in a superposition, and then you look at sort of the gradient of an entropy function in order to decide which task reduces the entropy the most, so which task is the most certain about a particular data point. And that you kind of infer that that's the task you're going to go with. So instead of the entropy, which is, well reasoned, they had this other objective they call a G. And G basically looks at it's really strange, it looks at the superfluous neurons. So they also add these superfluous neurons, these S neurons right here. And the G objective will only look at the S neurons in order to decide whether or not that's the correct task. And it's basically just the log sum exp of the S neurons. And we had some intuition about them being, all small and so on, them being like outlier detectors. But there is an entire chapter in the appendix where the authors do a sort of more in-depth theoretical analysis of that, which, it's not necessary to do this for them, so I really enjoyed reading that, and that gave me sort of the better intuition of what this G objective does. So here they say the aim is not to formally prove properties of the algorithm, rather we hope that a more mathematical language may prove useful in extending intuition. Okay. So again, that's pretty cool. So they start off by saying you have your neural network is basically W, and it's this phi right here, and the W are the last layer's weights, which compute your logits. So Y is going not to be your class, but Y is going to be your logits, and P is going to be the probability vector over your class, which if you calculate this via a softmax is going to be the following expression right here. If you have a mask, right, then at least in the last layer, you can infer it as this right here. So you multiply the mask by these weights, and then that gives you your logits. So they say here they initialize the weights right here. Actually, they initialize they have no bias term, and they initialize the weights by this constant. So plus minus this constant. It's not really necessary to do that, but they do it right here. It makes the analysis also a bit easier. I guess it just works more well. If you have these masks in superposition, of course, you want to add all of these masks with the respective alpha weighting factor, then multiply by the weights, and that gives you your logits. So note that this doesn't necessarily only have to be the last layer's weights right here. You can view that as any sort of weights of the neural network if you formulate this phi correctly. So you don't think that they only apply the mask to the last layer. They do apply the mask to the entire thing. All right, now the important part here is what happens if we look at the derivative of g with respect to one of the alphas and take the maximum negative derivative of that g, which is that mysterious function that only looks at the superfluous neurons. So what they want, they kind of construct this g by principle. What they say is we want a function g that mimics the supervised loss, right? We want a function g that is kind of equal like the supervised loss if we had the task ID, right? And that's pretty cool because you know, the supervised loss, you sort of need all the information. You need the label. You need the task ID. So the supervised loss is unavailable, but we want a function g that in its gradient mimics the supervised loss. So they go about constructing this right here. They say first lemma, it's possible to construct a function g such that the gradient matches the gradient from the supervised loss for all S neurons. So for all these superfluous neurons. Specifically, we want that the gradient with respect to the logits, if the gradient to the logits is equal, that means the gradient to all the rest of the network is equal because the rest of the network goes through the logits, right? The gradient through the logits is equal to the gradient of the supervised loss to the logits for all the superfluous neurons and zero otherwise. So they say the zero otherwise is pretty easily done in math, you know, just simply set it to 0, and in the actual code, which you can achieve like this, where M indicates the superfluous neurons, so this is just multiplied here, and the other ones are detached, so there is no gradient flowing. This is the property that we only look at the superfluous neurons. And now we are going to show that the gradient is going to be equal. So they say if you had the supervised loss, which means if you had the label, then this would be your cross entropy loss. Okay, so it divides into this part where you need the label, and then this part here you don't need the label. Now you can pretty much say, look, the label is certainly going to be one of not the superfluous neurons, because the superfluous neurons are superfluous. They are never the correct neuron. So this is always going to be, you know, not the neurons we look at. So the gradient, certainly this is always going to be 0. Because wherever the gradient is flowing, that's not where this is 1. So the gradient of any superfluous neuron is just this thing right here. And that's exactly why they build the function g. So the function g has this exact gradient. The function g, if you derive it, has that same gradient as the supervised loss for the superfluous neurons. Okay, so it's sort of magic, but it's not, you know, it's not magic. So they need two more assumptions here to get the following properties. So for the first property, because now we want to have G be identifying the correct task. So we've already constructed G. Now we want to show that if we really do this, the gradient with respect to the alphas, then if we do it for a wrong task, for the task that it's not the task of that particular data point that goes into computing G, then we'll get a value that's probably lower than 0. However, if we derive with respect to the alpha of the correct task, then we get a gradient, a negative gradient that's higher than 0. Okay, so we're now going to prove that this, with high probability, really allows us to distinguish the correct task from the wrong task. And we need two assumptions right here. Assumption one is we assume that the mask learned on task I will be independent from the data from task J. If the data is from task J, then these are independent random variables. Okay, so it sort of means that the tasks themselves are kind of independent. But it's not the same requirement. But you can think of in the case of permuted MNIST or so, this is it's given, except if you consider this kind of frequency of brightness and so on. But if you have independent task, I think that this is given. That means that the features right here and the masks are independent variable. If the data is from task J, then the features and the mask from task I are independent variables. Sorry. The second assumption you need is that we assume that a negative weight and the positive weight are equally likely to be masked out. Okay, so this again you can think of with some regularity. This is certainly going to be given in a randomly initialized neural network. Note that when the features are 0, which will be the case for zero mean random features, before I said this was your neural network, this is your random neural network, right? And then you mask that and so on. If this is a randomly initialized neural network, then you can make a case that the expected features of those will be 0. It doesn't need to be the case, but you can construct it such that it is. So if you have the two things, right? If you have those two things, then you can prove the following. If the data X comes from task J, then when you derive by an alpha that's not of task J, you get a number that's smaller than 0 in expectation. And here, the crucial part is you reframe this gradient. You reframe. And what you'll see is that this here comes out. So this is a sum, and each element of the sum is going to be greater or equal to 0, which means that this thing is greater or equal to 0, which means the negative thing is smaller than 0. In lemma H1. Now we're going to look at lemma H1 to get an intuition of what's going on right here. So lemma H1 says if J is the true task and I is not equal to J, then this quantity here is greater than 0. All right, I restarted my tablet and we are back. So what's kind of the intuition behind why this quantity here would be greater or equal to 0? And honestly, in order to make it a bit easier, I first want to look at whenever I equals J. So whenever J is the true task and then I equals J, then we can sort of think of the opposite, like why this should be smaller or equal to 0. So consider this. This is the feature of the network of U, right? And then the EUV connects that to the mask at point V, and the mask at that point UV is either 0 or 1, depending on the training. So this this xi right here, that's going to be from the initialization, but the mask is going to be 0 or 1, depending on whether that feature contributes, whether this entire thing here contributes positively to the task or not. So the secret right here, why we can make a claim that this is greater or lower than 0, is going to be that the mask can only be 0 or 1. It cannot be -1, right? So if the mask is 0, then obviously this thing is going to be 0. However, if the mask is 1, what does it mean? If the mask is 1, that means that this entire feature right here, let's call it f, is positively impacting, is positively contributing to this particular neuron right here. So if the mask is 1, it means the addition of that feature, more of that feature, makes that logit go up, okay? So if the mask is 1 during training, it means that the feature positively contributes to the task. So if we look at the gradient with respect to this function, with respect to the logit, and the function basically means it just measures how high these superfluous logits are. Then why do we find a negative interaction there? Because if you look at the neural network and you forward pass, and this particular feature is important, and you look at the loss g and you backward pass through the logits, if it is smaller than 0, that means there is a negative interaction right here. So that basically means that if we make this feature higher, then in this case we make this g function go lower, okay? And that is the case for the correct task, because if this is the correct task and the mask is learned adequately, that means it should assign a low weight to the superfluous neuron whenever the input features, are of that task. And so it makes sense that this here would be a negative number, because what we want, if the mask deems the feature important in a positive sense, we want that if the feature goes up, g goes down. And that's exactly why we have the negative interaction right here, right? So the negative comes from this being negative. I hope this sort of makes sense. So if the mask is 1, the mask says basically if that feature goes up, the loss goes down. Now g is a measure of the superfluous neurons. The superfluous neurons should be small if the loss is small. So if this is really from the task and this feature is really useful, that means if we increase the feature, the g function should go down. And therefore, this product here is going to be most likely negative, okay? And the contrary is, analogous right here. If this is not of this task, the mask can either be 0 or 1, right? If it's 0, then this quantity is 0. However, if it's 1, it's more likely that the feature here, because its I is not the correct task, which basically means that this feature, it is for a different task. It is good for a different task. So the mask of that different task says it's good right here. And we have no reason to believe that this would decrease the loss of this particular data point in this task. So it's kind of the inverse reasoning. If you look at the actual derivation here, it's fairly long, and it goes over the cases of the interactions between actually this initialization and the mask. So the initialization can be positive or negative, as you can see right here. And I just think that the intuition here is that the superfluous neurons react differently to a data point of the trained task because they have been kind of made to decrease for that task. and for that particular mask as they do for when the data point doesn't match the mask. When the data point doesn't match the mask, there is no reason for the logits of the superfluous neurons to be low. And if the data point task does match the mask, there is ample reasons for those to be low. I hope that sort of makes sense. It's a bit more of an intuition, but if you really want to dig into it, look at the derivation right here. Okay, second point is the fact that the masks and the superpositions don't really have to do anything with each other. And that's, I've said throughout the video, like, remember these tasks are super easy, yada, yada, yada. So let me make it clear in this diagram right here. The supermasks, these are simply a way to train a neural network in a crude way, right? I don't think there is, this distinction between mask and network, I don't really like that much, because ultimately what you're doing is simply you're training a neural network in a kind of weird way. Okay, the fact that you always use the same underlying, gray neural network doesn't really matter right here. It's still what you do in this supermask training is you provide a severely over-parameterized network, and then the mask simply gets to choose which weights to mix rather than you get to adjust the weights. If you adjust the weights, you usually get more accurate than with the mask, but it's sort of like a quantized neural network that you train right here. So that's the supermask thing. Again, I don't think it's important that the underlying network is always the same. The only advantage you have is it saves space because these masks are very small. The supermasks, on the other hand, this idea that you overlay all of the masks together and then you look at where this at the gradient of the entropy, and you look at which of the mixing factors the gradient pulls the most, that's a different idea. And the question here is, isn't that independent? Does it really depend on the masks, or doesn't it? And the hypothesis would be that if I simply train 3 different neural networks for 3 different tasks, could I not do the same superposition trick? Like, could I not just add all of them with the respective alpha, look at the entropy, calculate the gradient with respect to each of the alphas of the entropy, and then decide which task it is? Don't need masks, simply mix neural networks in superposition. So I did it. And I actually tried. Their code is available, so big props for their code being available. I tried their code. It's actually very few changes, and I'm going to append my live coding of this at the end of this video. So if you are interested in watching that, you can do so. But the outcome is, if I train neural networks, and I've done super quick and initialized them wrongly probably and all, but if I train these if I train the masks, you get to like 92% accuracy in their tasks, in each of the tasks, and then also in the average. If I train the actual neural networks, I get to a higher accuracy, like 93 something. It doesn't matter, it's just higher, okay? So that's hypothesis 1, is the training masks is just a way of training neural networks. The fact that the masks and the network training itself are that close, I think, is a testament to how easy these tasks are, like how easy MNIST is. I'm going to also hypothesize that if the task gets harder and harder, and I don't mean 10 class ImageNet, I mean 1,000 class ImageNet, then these masks are going to degrade severely versus training the actual neural network. I might be wrong. I mean, you can over-parameterize really heavily and they will still work. Okay, but in any case, I trained these neural networks and they reached higher accuracy, and then I did the exact same thing. I laid them in superposition to determine what task it is, and I could achieve the exact same result. So here in their example, they have 100% task classification accuracy, and I reached the exact same thing. Code worked. I'm not going to try to scale this up to 250 or 2,500 in tasks, but I'm going to assume that with tuning and stuff, that it's going to work about equally well. You could make an argument that the masks being sparser, they might be differentiated from each other more accurately, but I'm not sure. Maybe. but it's not a qualitative difference, right? So these two things are really two separate ideas that find their way together in this paper, but ultimately have not much to do with each other. Okay, at least that's from what I can tell. I might be wrong here, and I might be wrong with respect to their G objective and whatnot, and but I think that these are two cool ideas, but they can be applied independently. So, yeah. The last thing I want to look at is their broader impact statement right here. Now, there is a reason. So, usually I kind of track these broader impact statements because I think this here is sort of fundamental research, right? This is fundamental machine learning research. We do architecture, we do multitask learning. Task isn't really important as long as we have kind of the same tasks right here, uncorrelated and so on, the same hardness. And I've also made the point that it's really important for these tasks to be the same hard for this to work, and this plays a role right here. So, and they do describe some of this in this conclusion with, limitation that we observed has to do with task identity inference when models are not well calibrated, models that are overly confident for the wrong task. Okay, so in order for them to infer the correct task, so if you look at your entropy of the models for the tasks, that means you're going to select the model that is the most sure about the task. This only works if the tasks are equally hard, okay? If one task is much, much harder than the other task, this other task is always going to say, well, I'm really confident about this one because the task is just easier. It's going to train a neural network that's generally more confident, and you're going to misclassify a lot of the tasks. So here, what does this have to do with the broader impact statement? If you look at the broader impact statement, what they say right here, so they say, a goal of continued learning self-multitask with a single model. However, it is not exactly clear what qualifies as a single model. Therefore, a concrete objective has become to learn many tasks as efficiently as possible. We believe that SubSub is a useful step in this direction. However, there are consequences to more efficient models, both positive and negative. So this is sort of what the community does. So there are three things that I've seen so far in broader impact statement. First, some people say this is not applicable to us, which I agree. For most fundamental research, the broader impact statement is supposed to be, what does this particular method, how will this influence broader society? So not applicable, completely valid for most of these research papers, because guess what? You can use any method to do good or to do bad. And that's the second part. Second method is basically you just say generic statements how you can do good and bad, and usually you can't relate it to your particular method in the paper, right? Because your method is, I don't know, like my faster convergence rate of SGD. And so what you do is you just go one level up. You go up the levels. So it's like optimization can be used for good and for bad. I mean, that's still kind of a bit vague. And then you go up further. Well, optimization can do more machine learning. And machine learning can be used to do good and bad, for example, face recognition and things like this. So you just go up the levels. And that's what they essentially do here. And that's what, most people have defaulted to. It's like, okay, so, our model here is, basically one can train more efficient models. And then they simply highlight what more efficient models can do. Efficient models require less compute. Efficient model by be run on the end device. If models are more efficient, then large-scale research is not limited to wealthier institutions. By the way, also the broader impact statement, I believe, should be the impact on society and not really on the research community itself. This is a bit shaky with respect to, so I'm really regarding what the broader impact statement should be. This is not my opinion. I'm trying to reflect everything I've read of guidance about what the broader impact statement should be. By the way, there is also method 3, which is to simply tell me more about your paper in the broader impact statement, which I guess is the smart method, because the broader impact statement can be before the references. So it's in the main part, and people are required to read it, not like the appendix. Reviewers are not required to read the appendix. Reviewers are required to read the broader impact statement. So I guess the smart authors will just try to cloak more information about their model in terms of a broader impact statement, I guess. Well, whether that's smart is a different discussion. But here, it's already defaulting, right? It's already the default. People simply go level up, level up, level up until we can, say something generic. And we will also highlight and discuss the negative consequences of models which can efficiently learn many tasks, and efficient models in general. When models are more efficient, they're also more available and less subject to regularization and study of result. For instance, when a high-impact model is released, an institution will hopefully be accompanied by a model card analyzing the bias and intended use of the model. By contrast, if anyone is able to train a powerful model, this may no longer be the case, resulting in a proliferation of models with harmful biases or intended use. Taking the United States, for instance, bias can be harmful as models show disproportionately more errors for already marginalized groups, furthering existing deeply rooted structural racism. This is like, well, technology. This is basically a statement about technology. And so why do I have a particular, not issue, but why do I pick this broader impact statement? They even, this is this gender shades paper, right? Where people went and they looked at these commercial APIs for face recognition. I think that's the paper. Gender shades. So if you have a face recognizer, they realized they divided people up by, I think, gender and race. Like they built 4 groups, or I've just looked at the paper, but in my understanding that they divided people up into groups, which I find arbitrary to have these 2 axes, race and gender, but okay, you can do that. And they discovered that these commercial APIs have different accuracy for the different groups, right? And that basically their point is that, these commercial APIs, if they're offered for all humans, they should work equally well for all humans. Now you maybe see what it has to do with this paper. Well, this paper is in the business of doing multitask learning. So it is very viable to actually frame the task, for example. Like, this is an example. If you frame the task of multitask learning, like face recognition on different groups of people as a multitask learning problem, you have, group 1 right here, group 2, group 3, and then if at inference time, so you can build, good models for each of the group. At inference time, you're given an image and you're trying to infer first which group is that from, and then take the appropriate classifier. That would be, a hypothetical classifier for this thing. Now, what do we know about this thing? This thing fails if the tasks aren't equally hard. Also, in specifically, if for one group, let's say for group 3, the task is way harder because you have less data. I guess one of the main problems there is that the data sets are not equally balanced. If you have less data for that, then the task becomes de facto harder, and the model is less sure about the task, which means that it's a double whammy. So not only is the model itself less accurate, but the input data point, if the person is actually of group 3, is less likely to be classified correctly into the correct model to begin with. So, I've had my share of comments on the video I made, and I still maintain that societal bias comes about by data set. But for all the people saying there are models that exaggerate existing biases in models, this would be like, if there is ever any applicability of these broader impact statement guidelines, this would be the paper, right? It's this right here is an actual system that if I have different classifiers and I combine them with this method, it will double punish the classifier that is less sure, that is less accurate, because that is also going to be the one with the higher entropy, therefore not as much selected if I give a data point of that particular task. And so this is like I'm not criticizing the method here, like by all means, like this is a cool method where you can recognize that this happens and try to calibrate accordingly. But if there was ever any straight ball for a broader impact statement, I would, this is it. And this, I'm not saying that these authors didn't do that for a reason. I believe that, look, it's been whatever, not even half a year since we've started with these general broader impact statements, and everybody is already defaulting to simply say technology good, technology bad. That's people aren't even thinking. And so this is one of the reasons why I simply find these broader impact statements to be not a good idea, because there is a default answer and people are just putting it here, even in when there is an actual obvious, immensely obvious thing that they even cited the basis for that. So, that's sort of my take on this. I enjoyed this paper. The code is available. Everything is good about this paper. I'm not even the fact that these are, I think these are kind of two separate ideas. They're combined, cool. They're analyzed formally in theory. There's intuition given. All good. So don't get me wrong. This is not like trashing this paper. It's just I felt I had something more to say, and I think that was it. So yeah, I'll see you next time with a new paper. Okay, so our goal here is going to be to change this code to not use masks as mixtures, but actually use neural networks with real weights as mixtures and in superposition with each other. Okay, so what we're going to do is we're going to train the different neural networks and then use this kind of superposition trick to figure out which task a data point came from. So let's have a look at the code right here, and there's a bunch of helper code, and if we go down through everything, you'll see that this is the MNIST permuted dataset. So each task is basically a random permutation of MNIST, and if you execute, I believe, this here, and then you train the model, and right now it's for 5 tasks, but I guess that's going to be enough for now. Yeah, so if we get some good signal here, I guess it's a matter of doing kind of engineering and plumbing and tuning until you get it up to whatever 200 or 2,000 tasks, though I might be wrong there. So this is training, and I sort of had a look at the code, but I haven't actually tried this yet. So the model is built here. You see there's this multitask fully connected, which has these different layers right here, and it's built by these multitask mask linear models. Now the multitask mask linear models are defined right here. So it's basically a linear model. As you can see, it's derived from a linear module, and it has a parameter called numTasks, and then it has a parameter scores, which I guess is are these masks right here. And the scores, I'm going to guess, are always going to be multiplied by the weights here in the forward. So you can see there in the forward, you get the weights from the alphas. Yeah, this is the superimposed. All right. So if we know the task ID down here, we get this subnet, and we are going to multiply it with the weights. If we don't know the task ID, we want to get these alphas. So the alphas are going to be 1 over the number of tasks at the beginning. We're then going to multiply each of the alphas with the weights, and with that, we're going to get this subnet mask right here. So we need to know what this self.stacked is. So this self.stacked is getting right here in this cache mask. We're simply stacking this get subnet for all of the things. So our plan is going to be that this subnet right here is going to be the actual weights of the neural network, okay, and not just the mask. And then we don't need to actually multiply it with the weight. We can just forget about the weight, honestly, and just train the subnet. So for the subnet, as you can see here, you have this get subnet thing, and that's an autograd function, which basically means in the forward pass, you want to discretize it, and in the backward pass, this is a straight through estimator. So our first task is going, and this here should be done now. My laptop has stopped breathing. So we've trained 5 tasks, and now we can run inference on that. So this is when the task is given. Real quick, you can see task 1, 92%, 92%, 92%. 92%. So we have an overall performance of 92.44%. Then when the task is not given, we have 2 things to evaluate: whether or not, basically, how good we are overall, and whether or not we get the tasks correct. Of course, the tasks correct is a pre-requirement. So we have 100% task inference accuracy. Okay, so okay, we could evaluate this here, but you can already see the output from last time. There's like no difference from the performance of when the task is given. It's always being able to infer the task. We want to check out the same thing. So we want to change, first of all, this get subnet. This is where these scores are discretized. Now, given that these scores are going to be end up being our actual weights, we don't do that. We simply return the scores. Now this is pretty pointless right now, but we'll keep it just to be as close as possible to that. Now mask init, this is where we initialize the mask. Now this is timing uniform, and it has some thing, but we want to train the neural network to be initialized, as we know it. So let's try, what are other initialize functions? So init dot, what do we have here? Do we have, what's usual? I don't even know. Normal? Xavier? That sounds about right. That sounds about right. All right. So scores, and yeah, let's try this. This could like break everything, right? If you initialize wrongly, you get like dumb results. So okay, signed constant, yada yada yada. Where is that used? Okay, that's also initializing something. So we calculate the gain, and then, okay, this doesn't seem good. We'll just keep it. Hey, why not? Why not? Why not just keep it at that? All right, so cool. Oh yeah, this is for the weight anyway. We won't use the weight at all of this layer. We'll just use our own weights. So here we have these stacked. Okay, we get the scores. That's all good. Like, I'm pretty happy with that. I'm pretty happy with this mask init that we make our parameters. So these are going to be our different neural networks that we train. This all looks good. The alphas look good. Now, the only thing we want to do, honestly, is just to have not the weight times the subnet here, but the subnet as such, like this. Is this it? do we now train actual neural networks? I have my doubts, honestly. Like, there should be... No, this should be it. Yeah. Let's just try it. Like, we're gonna get a mistake somewhere, like a crash. Nope. Okay. All right. We're actually training. So, for real, like, these scores right here, the fact what made them a mask is that we discretized them right here. So we made them into a mask right here. We're not doing that anymore. So we're just training floats, and then we're also not multiplying it by the weight. We are just using those floats, which means that we are using the basically a neural network. And then here the bias, I was worried about the bias, but the bias is always 0, as you can see here. So the bias is always false. Yeah, so we're training 5 different neural networks for 5 different tasks. And, you know, according to my hypothesis, these masked things are just kind of crude, quantized ways of training neural networks. And if my hypothesis is correct, this here is going to turn out probably even better than this masked thing. Okay, so last task training right here. Laptop starting to breathe. Good laptop. Fast laptop. Very nice. Come on. And we're done. So again, we have an average top 1 performance of 92. Is this, did I even, oh no, I ran this right here. Okay. Like, that's the exact same number it was last time. So we need to run inference again. And if we're given the task ID, then we are at 93.9%. So we increase slightly, which might just be due to the fact that we initialized terribly. Okay, so what does it say about our task inference accuracy? Maybe there's some mask here. Set model task. The alphas are to 1. Nope. No, we're good. Task inference accuracy 100%. And I'm going to guess, well, with the task inference accuracy being 100%, I'm going to guess this here will give us the exact same number, like the 93 point some percent. So, yeah, 93.9%. So I'm going to say right here that the supermasks and the superposition really are 2 separate ideas, right? It's because the paper is like, it sounds cool and all with the supermasks and superposition, but this inference using the superposition and then the entropy to decide is really one idea, and training different the advantage in using supermask is, of course, that the model is way smaller. So you can remember it much more easily. But also, you know, it's really different. It has nothing to do with the superposition. Yeah, all right. So I'm going to guess this also works for, 200 tasks and whatnot, the higher order of tasks. So I think that's it, and we're done here.